so you don't see that. And I'm sharing my screen. So current's just going to be what we call a moving charge. And the equation we're going to use for current, and current is I, the variable is going to be I. The equation is how much charge, or coulombs of charge, will flow through a point, so give me your attention, per second. So we'll, like, let's say, pick a point, and if I say there's 2 amps of current, which you'll see in a second, that's what we call current, the unit for current is amps. Well, there's going to be 2 coulombs of charge that are going to flow through that point every second. So the new unit, so current, the variable you see in the equation is I, and then when you're done, when you solve for a problem, you're going to use the term ampere. You're going to have the variable A afterwards. Often we'll just say amps instead of amperes. So I already talked about that. Voltage. Okay, voltage is related to flow. When you hear voltage, think of it. Think of having a lot of electrons in a certain area versus not having many. And what would these electrons want to do if there was a lot over here? They're going to want to flow, right? They're going to want to go away from each other. They're going to want to go that way. Well, if we have less voltage, just a couple here, they're not going to want to flow as much as having a higher voltage. So when you think of voltage, just think of having this it's kind of like a pressure to want to flow, pressure for current to actually occur. So the higher the voltage, the higher the current would you probably have, but we're going to look at resistance too. Resistance, there's a pushing back. There's certain things that in a wire, or any time you're flowing, you have electrons flowing, that they're going to be resisting that voltage, and therefore the product of all this is current, the actual flow that occurs. So I'm going to use this water tower analogy. And so just take a look. When you think of voltage, think of like having, what happens when you find a water tower? Where do you find a water tower in the first place? Yeah, it's usually really, really high up, because the higher up, what you're doing is once you get water there, it's going to want to flow. So the higher the water tower is, the easier the natural flow is going to be just to your home and to any other place possible. Well, so you have increased voltage, you could think of having a higher water tower, and then resistance, think of the pipe that's going out of it. Which one's going to have more resistance, a bigger pipe or a smaller pipe? Smaller pipe. If you have a smaller pipe, you're going to have less flow that can occur. So it doesn't matter really how much voltage you have. If you have almost no, a pipe that doesn't let really anything go through, it doesn't matter how much voltage you have, you still won't have much current. So current is a product of having a high voltage and less resistance, and you're going to have more current. So stay focused in class. Stay off your phones. So let's look at reality. Let's look at what really increases resistance in reality. And there's 4 things we're going to look at: thickness, length, material, and temperature. And so what I'm going to want you to do is I'm going to want you to be able to tell me, if I ask you which one increases resistance, I need you to answer the question. If I say which one increases the current, well, you should be thinking opposite: less resistance, more current. So just on your paper right now, just on the side of your paper, go ahead and put less resistance, more current. Because if I tell you the resistance is high, you should be thinking less current. And if I said, I might ask you about current, I might ask you about resistance. So let's look at these 4 things. First of all, material. Take a look at the wire on the right. You're not going to get as much current through that thinner wire. So a thinner wire is going to increase the resistance, and therefore, what's it going to do to current? More resistance, what? More resistance, less current. If you have a longer wire, think of this. Think if you have like a point A and point B. Which one is going to occur quicker? This top one or the bottom one, getting from point A to point B? Top or bottom? Which one would occur quicker? Yeah, top one. So the longer the wire, if you have a longer wire, you're going to have more resistance, and therefore you're going to also have less flow. So longer wire is going to increase. Once again, on this slide, it's increasing resistance, and therefore what's happening to this? Increased resistance. Go ahead, next to that, put less current. And then the material of the wire. Not all materials are the same. You're not going to have a wire that's made up of rubber, because you're going to have nothing happening there. But even within the the metals, there's better conductors and there's worse conductors. So I'd rather have a copper wire than a steel wire. I know I personally went and bought a bunch of stuff off of Amazon because I don't like looking around for supplies. We all share supplies, and I like to do labs on the days I want to do labs when I think they fit. And so I bought a bunch of wires, and I realized they weren't that good because they were steel. And some of the things I wanted the students to see was not working out because I wanted students to test out the resistors, and what happened is the wire itself was a really big resistance, and therefore it just messed up the whole lab altogether. So I know in the future that I'm going to take a look and I'll make sure that I have copper wires or something that's going to be a little more conductive than that steel. So the material is going to be pretty important. And then this is weird, but higher temperatures are bad. Higher temperatures will increase the resistance, and therefore you'll have less current. So you might want to put a little note to that. A lot of times we think, okay, well, it's warmer, things are going to move quicker. Well, not in the case of this. When we have super computers, they're often going to be super cooled. They're going to have a lot of, they're going to get cold. They're going to be kept at a cold temperature because you want less resistance, so you have more current, so they can do that supercomputing. So this is just the opposite. So I'm going to pretty much say what I said before, but in the opposite order. So which one decreases resistance? So go ahead and put down more current. I guess you already have it, but just go ahead and write it again. It's not going to hurt. Because what's going to happen is when you have a test question or quiz question, I'm going to ask you that question, and you have to, I'm going to phrase it either in the terms of resistance or the terms of current, and you have to be able to connect the dots. So wire to the wire, that's good. We're going to have more current. The wider the wire, I'm going to get more electrons through there. The shorter the wire, that's going to be good. The better the conductor, that's also going to be good. Once again, less resistance, more current. And then if I can keep it at the lowest temperature, that's also going to be good, and I'll have the most current out of in a wire that I want to flow some electrons through. So we're going to look at all these different symbols. You do have to recognize these symbols, but you need to recognize this one right here. Take a look right there, that little big line, little line. Maybe let's go ahead and draw it. Go ahead and draw it again. Just a big line, little line, and next to the big line, put a positive. Next to the little line, put a negative. So with the battery, we're going to have a long side, and that's going to be considered, and I'm just going to go write it in here. The long side is a positive terminal. The shorter side is going to be a negative terminal. Often, we might have two batteries. Go ahead and do this as well. This would be two batteries. What do you think I'm going to have to do if I want three batteries? Yeah, just repeat it again. So when you have like an engineering scheme, some of you might be taking an engineering class of some sort, or you might in the future. I can kind of add every time I have a big line, small line, that's going to be a battery. Also, sometimes you might see like a power source, but we're going to pretty much pretend like batteries are our power source. But in general, we have the power company that's providing the electrons that are going to flow. We call the positive terminal a cathode. We call the negative terminal an anode. I'm not going to be very particular with my definitions from my class. But they're going to provide the source of electrons. The only thing here, this is what's going to be weird. I know we always talk about electrons doing the flowing. Well, Benjamin Franklin kind of started this off. He thought of this things. He thought that there was current, like what Benjamin Franklin did, right? With the whole, we had the kite out there with the key and all that. Well, no one knew anything about electricity then. So he decided there's this thing that's called it a positive flow. So he didn't know electrons flowed at that time. He just called it a positive flow, and it's something that we've kept up with. So in reality, electrons would flow from the negative terminal to the positive terminal in reality, but we're going to ignore that because it doesn't matter which direction they flow as long as they flow. They're going to power all devices. We always go from positive to negative for our convention. So when I say convention, it doesn't always mean it's right. It just means that's what people agree on. Everybody with me on that? So electrons are the ones flowing. We just pretend that it's flowing one way when it's really not flowing that way. But anytime we follow the current in a circuit, we're going to go from positive all the way back to the negative. And in fact, this one wouldn't flow at all because we have an open switch. When a switch is off, it's open, and an open circuit doesn't have a flow. So here's a fuse. A fuse is a temporary device. They're often rated, if you ever went into your car's fuse box, if you maybe a light in your car or light in someone's car went out, You might want to check the fuses first. And you might see a 2 amp fuse. You might see a 5 amp fuse. I'm not sure if there's a 2 amp, but there's definitely 5 amp. There's 10 amps, 20 amps. And depending on if you want to power a device that needs a lot of electricity, a lot of current running through it, well, you're going to have a pretty substantial wire. And you still don't want too much current, because when you have too much current, you can burn something out. With current comes heat. And if something overheats, what can that cause? Overheating something can cause what? Fire. It can cause fire. It can cause something in the device to melt. And if you have a device in your car, let's say a radio, it's a $500 radio, well, you might rather destroy a couple dollar fuse than a $500 radio. So fuses are these temporary devices that are put there, and all there is a little filament. And what happens is when there's too much current, this filament heats up too much, and this filament is going to get destroyed before this wire. This wire was going to take a whole lot more, and it might take up too much current where something else in the circuit is going to go out. It's going to get burned out. But we would rather destroy the fuse and just go replace the fuse and replace something else that's going to be more important, or everything if it catches fire. So it's more of a temporary, just next to fuse. Go ahead and circle a temporary safety device. Circle that. That's going to be important here. You might be asked the difference between a fuse and another one, which is a circuit breaker. So a circuit breaker, what it is, I'm going to draw. I'll draw a wire, and I'll draw, let's say, another wire. And what's going to happen with a circuit breaker, I'm going to draw it at a different level. With a circuit breaker, it's this bimetallic strip that, let me go ahead and draw it right here. It's this strip that has two metals on it, and two metals that expand at different rates. What's going to happen if two metals expand at different rates? You're going to have a what? You have kind of like a bending that occurs. And so what's going to happen is as the wire gets hotter and hotter and hotter, the bending's going to occur this way. And when the bending occurs this way, let me draw it a little bit shorter. It'd probably be really close to it. When the bending occurs that way, what's going to happen if it gets too hot? Well, at some point in time, this bending's occurring. It's going to push itself through, and when it pushes itself through, it's going to go down here. And this wire, if it's open, is not going to be working. This circuit that's open is not going to be working. And so what you're going to do is you're going to go down your basement or wherever you have a circuit box, and you're going to go ahead and you're going to flip that circuit box. The circuit breaker is going to not be in the right spot. And when you do that, essentially you are resetting this and putting it back over here so that it will go on again. Now, anytime you have that happen, if you ever have a fuse go off, you know how annoying it is? You go back, flip it back on. It goes off again. You go back, you flip it back on. It's doing you a favor. You really want to just give it time, because it's a product of heat. If that wire is too hot, that's why it's flipping. So you really have to watch out. If you keep on flipping that fuse box over and over and over, and something with the safety device doesn't work, that would be the bad thing, because you probably destroy a device or maybe even start a fire. So you have to watch out for that. But a circuit breaker is more permanent. So that's kind of the benefit of a circuit breaker. It's going to cost a little bit more, but it's more permanent. There's more to it than just a fuse that burns out. A load can be anything that uses electricity. It can be a light, it can be a radio, it can be a TV, it can be whatever you want. But a load is just a general term for something that's going to have electrons flowing through it, and it's going to take on that flow and use that electricity to power the device. A resistor. So a resistor, this is what you're going to get used to drawing. So I'm going to draw a quick resistor, really for the sake of us doing this lab. Let's go ahead and quickly do this. Go ahead and draw a battery with me. Draw a line. Go ahead and draw another line, and just go and give it a squiggle. I don't care how great you draw these resistors. Another line, draw a squiggle, line, line. What I just drew is a schematic of a battery in series. We're going to talk about series in a few days, with two resistors. So we have a battery that's in series. We'll talk about what that means, with two resistors. And we're going to do a lot of problems, little puzzle-like problems in this unit, where I start you off by drawing a quick diagram. And it doesn't matter. This circuit right here would act the same as this circuit right here, would act the same as this circuit right here. It doesn't really matter where these resistors are. It's gonna slow down. We'll talk about that another day. That's a future lesson. So it doesn't matter where you draw those resistors, but we'll talk about that. An open switch. An open switch is just drawing little two dots, and instead of a closed one, an open switch, we would just go ahead and draw it like this. Pretty much the two dots with an opening would be considered an open switch. And with a closed switch, the only difference is that we're going to go ahead and we're going to have that line down the middle. And so for a circuit to be working, and I want you to write this down on the paper somewhere on the side of your paper. You need a closed circuit for it to be on. Closed circuit for it to be on. So that's definitely going to be a question on a quiz or somewhere else, and you'll have that written down on the side of the page. You need a closed circuit for it to be on. So this top circuit is off. This bottom circuit is on. And often you have a more complicated, I could turn off these lights from that side. I could turn off these lights from that side. I could also turn them on. So there's more to these circuits. There's in the wiring and how they're done. There's multiple types of circuits and like how they're wired, so that they work certain ways. So we're just talking about a simple circuit, something that we might connect to, a couple lights and lights to a battery in this class. Open circuit's off, closed circuit is on, and then what happens is once you have a closed circuit, there's electrons everywhere, not just in one spot. And you turn on this electric field and everything starts moving. So it's not like you have power coming from let's say the power plant's right here. It's not like there's this power plant and once you close the circuit that everything just starts here and starts pumping through. No, what happens is there's electrons everywhere and electrons everywhere start pumping through. So the power plant's going to provide extra electrons, but electrons everywhere are just going to start moving. Electron drift, the reason why we have a wire that will heat up is because electrons, they kind of know where they're going, but they don't go directly there. They bounce all over the place and they're bouncing. All that extra moving around is going to create heat. Heat's going to be a side effect. You might want to circle that. Heat's a side effect of electron drift. More current, more electron drift, therefore more heat, and therefore possibly more danger. But in most cases, if you had someone smart plan out the device, and you use the right size wires and everything else you needed, you didn't have any short circuits, then you're not going to start a fire. You're going to not have as much heat. Two types of current is going to be alternating versus direct current. So what's happening at your power from the power plant is going to come to your house a lot better in alternating current, where it's going to be going back and forth, back and forth. And then once it gets to your house, it's going to be switched on by most outlets to direct current. It's probably getting beyond what I'm going to ask you in class, so I'm not going to spend more time right now talking about it. But power comes to your house, and often you might need to go between this alternating direct current. You're going to see what that means in a second. And you might have other devices like diodes, where in another engineering class we'll talk about it. But diodes can help regulate the direction of flow of current. Power sources, we have batteries, which we drew before, a line, and it doesn't matter. It doesn't have to be this way. It could be this way. If I have a big line, small line, big line, small line. But also you might see other ways of drawing it. Our common outlet's just going to be providing the same sort of electron flow that would happen from a battery. So here's direct current. Why would you call this direct current? Let's just take a look at two together. Look at this. See that alternating current? What's happening in direct current? How is direct current different than alternating current? Yeah, it's just one direction. If you have a simple battery pumping electrons, this is what's going to be happening. But there is this thing called alternating current. You know, the device doesn't care. These lights up here, they don't care if it's direct current or alternating current. If there's enough flow going through them, it doesn't matter if it's going back and forth like, it doesn't matter if it's going back and forth like this, or if it's going directly through it. As long as electrons are flowing through the lights are on. So just for alternating current, you're going back and forth. For the sake of just trivia, 60 times per second is standard in the US. But if anybody's traveled around, there's a couple different things in electricity. If you go to Europe, can you usually use your normal plugs from home? No, you're probably going to need something else, even if you go to the Caribbean, if you jump on a cruise ship. For you know, they often will have a lot of different devices. There's a lot of different things going on. Just because in the US it might be 60 times per second, it still works itself out, but the numbers might be a little bit different. So once again, back to conventional current, we're going to pretend like it's the protons that flow, or we'll call it a positive flow, but in reality, it's not. Just for the sake of convention, we'll always follow current from positive terminal to negative terminal. And that gets us to the question, so we can get to watching the video. And then tomorrow I might put a limit to how much you have to do, because I don't want to overwhelm you on a digital day. But we're going to start watching a video in a few minutes after we're done with these questions. So let's go ahead. Let me get those questions. You can put your heads up, those of you that have fallen asleep. I'm going to talk too much without enough questions. Let's go ahead and do this first one. How much current do you have when 50 coulombs of charge flows through a point every 25 seconds? So how much current would you have? And I didn't go with, I should have wrote down a givens list. I probably should do that. So you have charge, 50 coulombs. You have time of 25 seconds. You get 2 amps. So you'd have 2 amps. Okay, so a few more questions. See the cell phone's coming out. Let's try to stay focused. Which of the following increases resistance in a wire? This is where you have to watch out, because I could say decreases in resistance, and this is where also when you're taking a quiz or test, it will often be changed. I was trying to be nice, and I try to keep the questions pretty standard, pretty close to each other, and I just switched the words around. A lot of people failed. Make sure you're not, like, you make sure you're doing your own work. A lot of tests that are pretty easy that I have to do little subtle changes from one to another, and you have to be ready for it, because it will really help you think about the question and get it right. So which of the following would increase resistance? Yes, having a thinner wire. So shorter wire would decrease resistance. And also I could say increase, what would I say? By saying increase resistance, I'm really saying decrease what? Current. So this is where also I want to get you start thinking about this. That's not how you spell current, but you know, I could say a lot of different things to get to that answer or make it a different answer. So let's go ahead and answer the next one. Take a second, think about these. Which would increase current in a wire? Pick your choice. Having a lower temperature. So try to go in pencil, try to pick your next ones. Just go ahead and finish it off. And I'm just going to go ahead and go ahead and answer all the questions through the end. This is the last of the lesson for today. Oh, there's no questions? Did I not? Okay, I need to fix it. Okay, for now, let's go ahead and answer the questions that I have up here. Let's go at your pace, and I'm not going to go jump straight to the answer. And I'll go ahead and update that so that I do have these questions. What's this safety device? It looks like this is going to be called a what? It's going to be a fuse, yeah. So this is where you might have to recognize different things. It's going to be important. This special device is used to decrease current. What's that going to be? It's going to be a resistor, yeah. So I'll update the notes and just throw them online. If you want to reprint it, you can. If not, it doesn't really matter, as long as you know the answers. This device is any generic device that we use out there. It's going to be allowed, yep. Which model would represent the best alternating current? Yeah, it can be A. Why is that? Why is A better than B? Yeah, because you have the arrows that are representing the direction of flow. Okay, so you have that little half sheet, and I will probably limit the amount. So what you're going to have to do tomorrow. For a digital day, there's a video that's on electricity. Tomorrow, you're going to have to finish off to a point. I'll go ahead, and after we're done watching this today, I'll decide, okay, finish through question 6 or question 5. And then you're going to have to put it, and you're going to have to upload it onto the e-class. So it's going to be it'll be a Dropbox that you're going to have to use. So just be prepared for that. You'll use the Dropbox, and then that will be that'll be it. Let me go ahead and pause this video.